Jai Hind. Myself, Dr. Uma Sharma, Assistant Professor in EC Department of Ajay Kumar Garg Engineering College. In this lecture series, we are discussing the complex topic of VLSI design. So, this is lecture number 4. Here, we will discuss the Dynamic CMOS design. So, here we will see what is the basic difference between static and dynamic design, and what are the various advantages of using dynamic CMOS logic style or design, and we will see the operation of dynamic CMOS logic. So, these are the outline of my lecture. Here we will see all these things, and the important thing is here we will see the domino logic as well as the pass transistor design style too. These are a very important topic of unit number 4 of VLSI design, that is BEC 701 code. So, first of all, let's see what is the dynamic logic design. So, basic dynamic logic design is methodology for the digital circuits. By using the dynamic logic design, we can reduce the number of transistors in any circuit if we compare the design structure with the static. So, this is the primary goal of the dynamic logic design, is to reduce the transistor count and hence increase the speed of the circuit. Okay. So, here if I compare dynamic with static, in case of static, there is no need of clock, but the dynamic design operates on the basis of clock signal. So, here the clock play a very important or significant role. This slide shows the basic comparison between static and dynamic. From exam point of view, this is very important. You should know what is the exact difference between static and dynamic. So, on the basis of various features, let's say like output state. Here in case of static, it is always connected to either VDD or ground, but in case of dynamic, it is floating or temporary floating. So, output node is floating, like it is not always connected to VDD and ground. Once the output node is precharged, then with the help of capacitor, the output node maintain that particular charge. So, this is the basic difference in output state. Similarly, if I talk about the circuitry, so in case of static, it uses pull-up network and pull-down network, whereas in case of dynamic, the PMOS transistors are used as pre-charge circuitry, and the main circuit is implemented using the NMOS transistors, and here we use generally the pass transistors. So, in this lecture, we will also see what is the design of pass transistor. Third feature is the transistor count. In case of static design, the transistor requirement is very high. For example, if we implement two input NAND gate, NOR gate, then definitely we require 4 transistors, whereas in case of dynamic logic, we need only 3 transistors. And if I talk about the large number of inputs, suppose n number of input, so in case of static design, we need 2n transistors, whereas in case of dynamic, we need n for implementing the main circuit and 1 transistor is needed for the pre-charging. So, you can see the difference between both. Then speed, obviously the transistor count is large in static, so speed is less, but in case of dynamic circuit, the number of transistors are very less or fewer transistors, that is why speed is very high. If I talk about the power, so in term of power, static design is better, because here the static power dissipation is 0 if I talk about the CMOS technology, whereas in case of dynamic, the dynamic power dissipation is very high. In case of static is 0 and dynamic is also very less. So, overall I can say in static power dissipation is low as compared to the dynamic, but here transistor count is less. So, we can see if transistor count is less, then power dissipation will also less. clock is not required in static, whereas dynamic clock is required. If I talk about the noise immunity, so noise immunity is also very high in case of static, but they are very susceptible to noise in case of dynamic. So this is the general structure of the dynamic logic circuit, where you can see that this is the PDN. Here we can implement any logic expression with the help of N type of transistors, because this is N type network. So the PDN is made up of N type of transistors like NMOSes, whereas this is known as the precharge transistor MP, and this is PMOS, and here clock signal is applied. This is the evaluation transistor, additional transistor is there, evaluation transistor, and whenever clock is high, then definitely this transistor is on and this is off. Whenever clock is low, when this transistor is on and this is off. So at a time only one transistor can on. So here you can see that the circuit operates on the clock signal, and the first phase is known as precharge phase, and when clock is low, that means this transistor is on, and when PMOS is on, then output node, this node is connected to VDD, and definitely the output is equals to VDD in the precharge cycle. But this is not the final output. In case of dynamic style or dynamic CMOS logic design, we evaluate the output at the end of evaluation cycle. So the second cycle is known as evaluation phase when clock is high. So when clock is high, then this transistor is off. That means there is no connection between VDD and the output node, and if there is no connection between VDD and output node, that means the inputs, the output depends on these inputs. So whatever is the connection in this PDN, the output depends on that. If there is a direct path between output node and ground, because this clock is high, and if it is high, it means the ME is on. So now if PDN is complete, all the transistors in the PDN are on, that means output is connected to ground. So output will be 0. In case of the structure of PDN, and there is no direct path exists between output and the evaluation transistor, that means output remain at logic high level. So this is how we can evaluate the output node. So depending on the PDN, the output will be 1 or 0. So this is the operation of the dynamic logic structure. Now you can see that there are two type of dynamic logic structures are there. One is N-type network, second one is the P-type network. In N-type network, this PDN is made up of NMOSes, whereas in case of P-type network, the main Boolean expression will be implemented using the PUN, which is consisting of PMOS transistors. So here you can see that there are two transistors, one is known as precharge, second one is known as the evaluation transistor, and input is implemented through the PDN. In case of P-type, there is a evaluation transistor, this PMOS is known as evaluation transistor, and this NMOS is known as precharge transistor. So the function is reverse, and the input is implemented using the PUN, that is PMOSes. So we can take any of the logic structure for implementing the CMOS design, but generally we prefer this N type of dynamic logic design. So the next thing is, in case of dynamic logic design, there are so many issues. If we connect multiple stages, then definitely because of the clock, so synchronization clock is very important, and due to clock there are so many issues with the dynamic logic structure. So one of the problem is erroneous output. While cascading two stages, there are so many issues in the dynamic logic design. One is erroneous output. So here you can see that there is one stage, this is one dynamic stage, and this is the second dynamic stage, and both the stages are working on this clock phi. So you can see that once this phi is 0, then precharge phase will take place, and in precharge phase this node is connected to VDD. So this is high, logic high, and this node is also at logic high level during the precharge phase. So here from the waveform you can see that during precharge phase, this is precharge phase, MP transistors are on, so this is also high and output 2 is also high. But because of this cascading, depending on this input stage, or you can say the expression, the output 1 should change and output 2 should change during the evaluation phase. So what happens when if output of stage 1 is high, then output of second stage is also high. So there is no issue, but we want that output 2 should remain on the logic high level. But due to this pre-charging phase, that output start reducing, because still the input stage, first stage is having logic high, and it is logic high, and this circuit is behaving as an inverter, so that goes to the low, and originally it should be high, but it is coming out low. So this is known as erroneous output. There are so many other issues, and that issues are due to the charge sharing problem between cascading or multiple adjacent stages. So remember that the problem of cascading conventionally occur in the dynamic CMOS logic stage when one or two stages are making transition between 1 to 0. So this is the main issue of this dynamic logic design, and for this cascading problem there is one solution which is known as domino logic. So static design, there is no need of clock. In dynamic design, the circuit output depends on the pre-charging and evaluation phase, so depends on the clock, and very susceptible to noise, but transistor counts are very less in case of dynamic. If we want to cascade multiple stages, then there is a possibility of erroneous output in dynamic design, and to overcome this cascading issue in the dynamic design, we can move towards the domino logic. So this is the next evolution of the static logic design only. Like, we are talking about CMOS technology only. So in CMOS we have seen the static, we have seen the dynamic, we have seen there are so many issues in the dynamic design, and one of the issue is the cascading, and to reduce the cascading issue we can use domino logic. So what is this domino logic design? Basically in domino logic, this stage is nothing but a dynamic. After dynamic, we have added one inverter, and this is static inverter. So this is a combo of dynamic and static. So if we combine both these technologies, then it became domino logic style. So what happened? During pre-charge phase, output node is charged to VDD, and because of this static inverter, this node remain at 0. So when we are cascading multiple stages or there is a transition from 1 to 0, due to this inverter, this addition of this inverter, there is a reduced possibility of erroneous output. So in domino logic, we use inverter just after the dynamic logic design. So by inserting this static inverter, we can reduce the chances of erroneous output, but again at a cost of increased number of transistors. So this is the issue of domino, like transistor count definitely will increase. So this is one of the another important topic of this dynamic logic style, which is known as pass transistor. In the previous slide, we have seen that by using pass transistor, we can implement PDN or PUN. So if we use NMOS pass transistor, then PDN can be implemented. If we use the PMOS pass transistor, that PUN can be implemented. So, in dynamic logic style, because we need two inputs, like one input is main A, B, C, D number of inputs, and second input is clock. So, by using this pass transistor technology, simultaneously we can apply clock as well as the input signal. So, there is a significant role of pass transistor while designing the dynamic CMOS design. Okay. So, with the help of pass transistor, we can implement any logic expression easily with less number of transistors, and definitely the performance will also enhance because it reduces the number of transistor count, and definitely the transistor count is directly proportional to the area of the circuit. If area of the circuit is less, then power dissipation is less, and definitely the speed is also high. So, that will enhance the performance of that particular circuit. So, let us see the structure of pass transistor. So, this is NMOS pass transistor, and here you can see that this is the drain terminal, this is gate terminal, and this is source terminal. So, here the input is applied at this node and output is taken from this node, and this is the gate terminal, which is a control terminal, like, because this MP pass transistor is behaving like a switch. How? Because this is NMOS, and we know that if at the gate of NMOS transistor input is greater than threshold voltage, then transistor will become on as a on switch. So, like, I can, if this signal is high, that means this MP can be replaced by this close switch, and if it is low, then it can be replaced by this open switch. So, here this transistor is behaving like a switch, and you can see that if clock signal is low, then this transistor is off. That means there is no connection between input and output node, and there is no impact on the output by this input Vn. But when clock is high, so clock is high, that means we are talking about the evaluation phase. So, in evaluation phase, when clock is high, the input is directly going to the output node. Here the output node, this Vx, will be charged by this VOH, but due to this operation in pass transistor, this output is minus Vt, which is the threshold voltage of this VTH, you can write threshold voltage of this NMOS. So, in case of pass transistor, if input is high, we will get output which is at least having a drop of threshold voltage. So, this is the only drawback of using NMOS, because it is known as pass transistor. It is passing input to the output, but with a loss of threshold voltage. If I use PMOS, then in case of PMOS, the circuit will pass 1 as it is, but there is drop in 0. In case of zero input, suppose clock is high and input is 0, then definitely the output will all is equals to 0. So, NMOS pass transistor can pass 0 as it is, but it is not good in passing logic 1. So, sometimes this question may be asked in the exam. So, you can understand because of this situation. This situation is what? Because we want pass transistor must operate in the saturation region. So, to maintain this saturation condition, VDS should be greater than VGS minus VT. There is a 1 threshold voltage drop in the output always to maintain this saturation region. So, we can use this pass transistor very smartly to implement the dynamic logic circuit, because there is a very small drop of threshold voltage that can be considered as logic high. So, again by compromising on the output voltage swing, output swing of the voltage, we can use this pass transistor in the dynamic logic design to implement any Boolean expression. So, this is all about the dynamic logic circuit implementation of any Boolean expression. By using this concept, you can implement any Boolean expression by using this methodology. So, this is all for this lecture. In the upcoming lecture, we will see how we can use this pass transistor logic in the dynamic CMOS implementation.